Hello everyone, welcome to YouTube channel Energy Theory Applications. I am Professor Morosuk and I am the author of this YouTube channel. Today we are with the topic exergy. All lectures have a very dynamic style of presentation. Definitely some of you would like to learn more, particularly about exergy. We will be happy to answer your questions and provide with an extended information. Our contact email you can find in the description of each video. Please support our work with a like to this video, subscribe the channel and share the link with your colleagues. Lecture 6 in block exergy. Finally, we reached the lecture when we will start to discuss exergy analysis. Exergy analysis is quite long discussion. That's why today will be part 1 and next lecture will be part 2 in more detailed already discussion that today we will cover all these topics. I just would like from the beginning to mention that term exergy analysis and term exergetic analysis, both are correct and both can be used. Let us repeat the definitions of exergy. It is always useful to keep in mind all definitions of exergy. First of all, exergy, it is a combination of quality and quantity of energy. Exergy, it is measure of the deviation, the state from the thermodynamic environment. Regardless, we will discuss higher level of the thermodynamic environment or lower level of the thermodynamic environment. Official definition of exergy that it is maximum theoretical work that can be obtained if system will be brought to full equilibrium with the environment. Maximum theoretical work if we're discussing about system operates above of thermodynamic environment, and if system operates below of thermodynamic environment, then we will say that exergy it is minimum theoretical work. And the last definition, exergy is the combination of the first and the second laws of thermodynamics. Every time when we have a new analysis, we need to write balances because we already discussed it with you that mathematical model of the system, it is the set of balances. And general view of all balances used in engineering thermodynamics and also energy engineering, it is change of parameter equal transport plus generation minus destruction. And we know that never three terms will be together in the right part of this equation. We know mass balance where change in the mass is equal 0, mass in is equal mass out. We have energy balance, that change in energy associated only with energy transport. We have entropy balance when change of entropy, it is transport of entropy and entropy generation as measure of irreversibilities. And now we're with exergy balance. When change in exergy, it is the transport exergy through the system boundary minus destruction. So now we need to discuss the term destruction. We know that exergy cannot be conserved, and exergy is destroyed because of irreversibilities within a system. So it means that term the exergy destruction should participate in exergy balances and should describe the irreversibilities, because we cannot calculate irreversibilities. Irreversibilities always can be calculated and so numerically can be explained using the term entropy generation or exergy destruction. Now we're discussing with exergy destruction. We know the definition of reversible process. Process can be reversible, can be assigned as reversible only if system and surrounding will be returned to initial state. And we already discussed it that for system it is possible, for surrounding it is impossible to be returned to initial state. It means that we need to add other term that will discuss the irreversibilities within surrounding, because here in the balance, the term exergy destruction for us associated only with the irreversibilities within components. Now, how to include irreversibilities within surrounding? In modern exergy analysis, we have the term exergy losses. So exergy destruction, I will repeat, it is irreversibilities within the system, and exergy losses, it is the transfer of material stream or energy stream to the environment. So it means that it will be irreversibilities within the environment. Energetic analysis, of course, used by all engineers for energy balances, for simulation, and so on. But results from the energy analysis mislead the engineers because we cannot identify the thermodynamic inefficiency, or how sometimes people say real thermodynamic inefficiency. We can only discuss about entire system, but we cannot discuss about irreversibilities or inefficiency, general term, within each system component. How to avoid all these problems? We should proceed with the thermodynamic analysis where exergy concept is included. So we're calling such a analysis exergy-based analysis. So term exergy and exergy concept should be included to the thermodynamic analysis. An official definition is like that within exergy analysis or exergy-based thermodynamic analysis, we can identify location, magnitude, and causes of thermodynamic inefficiencies. So 3 goals of the exergy analysis: to find location of irreversibilities, their value, magnitude, and causes why these irreversibilities are taking place. And these 3 terms, location, magnitude, and causes of inefficiency, can be explained through the term of exergy destruction and exergy losses. Now a few words for very simple explanation exergy destruction and exergy losses that I always use it for my students. Let's assume that I will carry something with myself, some sort of goods, and everything is fallen down and broken. It is destruction. It is destroyed. Completely different if I will carry something and lose on the way. So for me, does not matter. This thing will not exist, but it was not destroyed. It was lost. So one more time, destruction, because we have this exergy destruction because we have irreversibilities within the system, and exergy losses because stream of exergy, material stream or energy stream, will be transferred to the environment. So let us discuss exergy balance of the closed system. I hope you remember our discussions within energy engineering, that there are functions, state functions, and there are path functions. That from state 1 to state 2, we can use different pathway to achieve the goal. Absolutely the same can be applied for exergy analysis. Let us assume that we have system at state 1 here, and after that, because of some factors, system moved to state 2. So from this example, we can also conclude that exergy is the state function. Okay, and the change in exergy between state 2 and state 1 will be associated with the effect of heat transfer or exergy exergy stream associated with heat transfer to the system from the system, exergy stream associated with work transfer from the system or to the system, depends on the system, and also the term of exergy destruction, because all processes are irreversible, and we have therefore we have the term exergy destruction. Again, the same equation, and now we need to discuss each of these 3 terms. Exergy transfer associated with the heat transfer, we already discussed that since thermal energy has quality, so exergy transfer associated with heat transfer consists of 2 parts, quality and quantity, and quality, it is the Carnot factor. Exergy transfer associated with work, mainly it is work itself, where the second term can be neglected or maybe even zero. And the term of exergy destruction, we know that exergy destruction and entropy generation both are describing irreversibilities, and the difference in these terms only that exergy destruction, it is temperature of the environment, multiplied to entropy generation within component or within system. And since here we're discussing about closed system, it means within the system. And definitely exergy destruction always can be positive or zero if we have ideal processes. And now the question, what means exergy destruction? What exactly we're destroying? And now the answer. A part of exergy that's supplied to a real system will be destroyed because of irreversibilities within this system. So destruction cannot be something hypothetical. This will be destroyed part of exergy that is supplied to the system. And in old exergy analysis, means earlier versions of exergy analysis, very often term exergy destruction associated with exergy losses, means that losses in destructions, many authors use different words for the same definition. Therefore, if you are using different publications of different authors and also books written by different authors, depends on the year of publications, can be the term exergy destruction and can be the term exergy losses, that destruction in fact and losses together. Therefore, it's necessary to check very properly the definitions and equations. So we know that exergy transfer associated with heat transfer can be zero only, this value can be zero only at the temperature of the environment. If we're above of the environment, exergy will be always positive. If we are below of the environment, exergy will be negative only because it is a direction of exergy transfer. Therefore, we should ignore the fact that it is negative value, and we should deal only with absolute value. Therefore, in this graph, we can see that both values are positive because in fact we are discussing deviation from the level of the thermodynamic environment. And now exergy balance of the open system. Let us assume that we have open system, sometimes call it control volume, or we can say that it is component level. We have exergy streams coming to the system associated with material streams, also going out associated with material streams, and we have thermal interactions with the surrounding or with other systems, and also work. And entire balance will be written as a rate of exergy change and rate, because we will discuss everything per unit of time. So we will combine, so we will write more complex analysis, not only exergy balance, but also immediately we will write this equation on time base. So rate of exergy destruction, it will be rate of exergy transfer associated with heat transfer, with work, incoming and outgoing material streams, and the term rate of exergy destruction. And now a little bit more in detail. So again, absolute the same terms. And now I would like to focus on the value of exergy streams incoming and outgoing to the open system or to the component. So in this equation, we have only sum of exergy streams and sum of, so incoming and outgoing from the system. But behind each of these terms, it can be total exergy as a sum of physical and chemical, but in general we can also write sum of physical streams plus sum of chemical streams incoming and outgoing, absolutely the same. Or if we need to proceed more detail with the exergy analysis, maybe it is required, then each exergy stream will be divided into three parts: thermal, mechanical as sum of physical, so as part of physical, and chemical. So in this moment, each stream should be multiplied by 3 different contributors of exergy, thermal, mechanical, and chemical, and of course analysis will be much more complex. All cases when we can use total exergy or only physical, chemical parts, or all three parts, we will discuss later. And this complex equation we can rewrite already under steady state conditions. So it means that time, so all variables will be constant during the time. And one more time, I repeat, exergy transfer associated with heat transfer, with work transfer, sum of all incoming exergy streams, outgoing exergy streams, and the term of exergy destruction as a measure of irreversibilities within open system or within the component. And now you can ask me, okay, but where is exergy losses? We continuously discuss about exergy destruction. Where are the losses? Because exergy losses, we did not mention before, it should be only for open system or for closed system. In general, how to proceed with this term, because it is exergy transfer to the environment. Again, we need to repeat our discussions related to selection of the boundary conditions to evaluate the components. That was a discussion on entropy, concept of entropy. And we know that for the component, now I'm discussing only components, systems are not included, we have two possibilities to assign boundary conditions. It can be boundary conditions fully repeat physical boundary of the system of the component, then definitely we need to calculate heat transfer through the system boundary, and each part of system boundary can have different temperature, or we can assign other boundary conditions where a little bit thermodynamic environment will be included to boundary, and temperature of boundary will be equal temperature of the environment. Then this is stream of entropy that is easy to calculate because we don't need to consider each part of the boundary, very complex boundary of the component. And what is the difference to assign different boundaries for us now for exergy analysis? In first case, case for boundary one, definitely the term of exergy losses exists, because it will be the same as transfer of entropy streams through the system boundary. And for another application of boundary, exergy losses will be zero, because heat transfer at the temperature of the environment, definitely it is, from exergy point of view, it is zero. Can we always say that exergy losses for the component will be zero for all cases? Unfortunately not. It is easy approach, but we cannot say like that, because if temperature, operation temperature of the component is very high, for example, for heat recovery steam generators, it can be even 1000 degrees Celsius or even more for coal-fired power plants, or maybe for some reactors in chemical plants, then definitely we need to consider exergy losses. Maybe exergy losses will be considered only for few components with very high temperature, and for other components can be this term neglected. This each particular case should be discussed for the system that supposed to be evaluated. But the same can be applied if we discuss about cryogenic system, particularly for hydrogen production, when temperature is really very low. It can be 20 Kelvin, 50 Kelvin. Then definitely also exergy losses will exist, and we need to include this term to the analysis. But I repeat, it is very special cases. So now let us return to this figure with open system exergy balance. So we have equation that we already discussed, that all streams should be considered. But for simplification of analysis, we can replace this complex equation with a little bit simpler equation. We can write that exergy incoming to the system, so it means that sum of all streams incoming to the system is equal sum of all exergy streams going out from the system, term of exergy destruction and term of exergy losses. And since exergy losses sometimes will be not considered because of boundary conditions, we can say that exergy, term of exergy losses, will be charged to the term of exergy destruction. So it means that we can say that exergy losses equal zero, and this value will be charged to term of exergy destruction. Then in these cases, exergy destruction will be overestimated, but nevertheless in out we will not destroy our balance, just one term will be merged with another term. This will make our engineering life easier. And one more time, I repeat, to include term exergy losses for the open system, means for the component, or not include, depends on the boundary conditions that we will select ourselves for each particular component. So now we are with exergy performance. We discussed very long absolute value, so the term that can be calculated, the magnitude of irreversibilities associated with exergy destruction and exergy losses. Definitely both are measure of inefficiencies. And if we would like to improve system, we have two possibilities. We definitely will work for the decreasing of exergy destruction, but also decreasing of exergy losses. It is the way to improve the system. But we need to evaluate the system, and sometimes we don't need absolute values, we need relative values. And this is a measure of performance. As measure of performance, we have three variables, and the most important, of course, it is exergetic efficiency. So now, again, we are with the system, and this system is designed in such a way that does not matter will we discuss open system or closed system. Let us make this analysis more general. So we have several exergy streams coming to the system. We have several exergy streams going out from the system. So, and now for us does not matter it is material stream associated with exergy or it is energy stream with exergy equivalent, does not matter. We have incoming exergy streams and outgoing exergy streams. We have exergy destruction as the irreversibilities within the system, and let's assume that we have exergy losses. So equation can be already rewritten in the form incoming outgoing streams, and the same equation also for incoming outgoing streams. And now we can see that only the difference in this equation, this subscript. In first equation, subscript tot, in the lower equation, subscript K. So this is the modern nomenclature for exergy analysis. When we have subscript tot, or sometimes people is writing system, but it is not correct because system can be open or closed. Better to write tot means total, and this is overall system, or closed system. This is strict definition from thermodynamic definition. And case component, so each component of the system. Usually uses the term case component and equivalent of open system. And as we already said, depends on the boundary conditions. Exergy losses can be merged with term exergy destruction only on component level. We're not allowed to do the same merge for the overall system. Term exergy losses for the overall system we will discuss very much in detail within coming lectures. But at present, please remember that losses can be charged to destruction only for the component. For the system, we always should have two terms for the description of irreversibilities: destruction within the system, and losses, it is transfer of energy or material stream to the environment. So again, we're with the same equations, and now we would like to calculate efficiency. So this is our idea, finally, to find efficiency of the system and also of the component using the concept of exergy analysis. Again, exergy efficiency or exergetic efficiency does not matter. Both terms are correct, and both terms you can find in publications. So now, please follow me very carefully. How we can write efficiency? We have only two terms, in and out, because destruction losses, it is inefficiencies, it is irreversibilities. We have only in and out, and we have only one possibility to write efficiency as out divided by in, simply because we have no other terms. And that was the approach of very, very, very early stages of development of exergy analysis. When just exergy analysis was introduced in the 60s, it was only one definition: out divide by in. But this definition is not appropriate. I would like to say from the beginning, it is not appropriate. And why it's not appropriate? Let us proceed with another slide. So again, we need to remember, as you can see today, we need to remember many things from the energy analysis and from the entropy analysis. In order to calculate energetic efficiency, it is called general term performance, we discussed that among all energy streams, I'm discussing energy analysis, incoming and outgoing from the system, we need to find streams associated with positive effect and streams associated with driving energy. And positive effect in energy term over driving energy, of course, in energy term, it will be efficiency from the point of view of the first law of thermodynamics, only based on energy concept. Now, we just discussed that if we have system with many exergy streams in, exergy streams out, and that was the only one way to write efficiency as all out streams divided by all in streams. But in this way, definition of exergetic efficiency logically will contradict to definition of energetic efficiency. I'm not discussing about calculations, only logically. Here we have positive effect driving energy, and here we have everything out divided by everything in. So one more time, I repeat, this is not appropriate definition. And people, of course, were working on the definition of exergetic efficiency, and also was the following idea: useful exergetic effect, something like a positive effect, and here driving energy, here driving exergy. But energy and exergy, we know it is not absolute the same. Therefore, we cannot copy paste idea from energy and put this the same terms just instead of energy exergy to calculate exergetic efficiency. Because what means useful exergetic effect? It means that there are not useful exergetic effects, but nevertheless it is exergetic effect. And what means driving exergy? That is also not clear. Again, this is not appropriate definition. It was short attempt. Exergy of useful products divided by fitting exergy. Again, misleading term. What means useful products? Similar to previous, it means that we have not useful products. And what means fitting exergy? Fitting exergy, it also can be all exergy streams coming to the system or to the component. So again, not appropriate definition. So when we are working with exergy analysis in terms in out streams, it's very not even very difficult. It is almost impossible to find appropriate definition that all authors can strictly follow, because if we have different readings of these terms, so it means that each person, each researcher can apply this term according to his, her even feelings, not even knowledge. And this is not a good idea to have so different opinion to conduct exergetic analysis. Now, why I'm discussing so much in detail all these inappropriate terms? Because even now in modern publications, people use it, this definition of efficiency. Because sometimes people using old books in exergy analysis, and they assume the definition of exergetic efficiency never was changed, and this is absolute proper. Therefore, when you are reading the book or publications related to exergy analysis, first you need to check always equations, which approaches of exergy analysis were used, and definitions behind all these calculations. So we can say like that these three equations, it is early approach simply because it was no other approach, but better don't use this approach now because we have something other more uniform. And what means modern exergy analysis? Modern exergy analysis now is dealing with different variables. If old exergy analysis or early versions of exergy analysis, we always discuss it in terms in, out, modern exergy analysis is dealing with the term exergy of fuel, exergy of product. These new terms and new approach in exergy analysis has been introduced already 40 years ago in 1984 by Professor Tsatsaronis, and now only this term in our exergetic school we are using exclusively exergy of fuel, exergy of product approach. And if we use approach exergy of fuel, exergy of product, then exergetic efficiency is always very easy to calculate. Product over fuel. Does not matter, system or component, always product over fuel. And now we need to discuss what means product, what means fuel. So again, we're with the same figures, incoming, outgoing streams, old version of exergy analysis and modern version of exergy analysis. Instead of dealing with some of incoming, outgoing streams, we will rearrange these streams. There is special theory how to rearrange the streams, and we will have two cumulative streams. One cumulative stream, it is exergy of fuel. It is not many streams associated with fuel. It is one cumulative stream, exergy of fuel. We have one cumulative stream, exergy of product, and we will have one cumulative stream, exergy losses. So now we need to learn how to find these cumulative streams when in real life, of course, we have incoming and outgoing streams. Does not matter for exergy analysis which method we will use, in, out, or fuel product. Irreversibilities will be the same, of course. So the method will not affect to the absolute values of irreversibilities to calculate, but of course method will affect to the appropriate definition of exergetic efficiency. And now system, closed system, and component. Equations are similar. Fuel equal product plus destruction plus losses for the system, and for the component, fuel is equal product plus destruction. So usually we assume that the exergy losses for the component 0, and only in very special cases we will calculate this value. But for the majority of components, majority of cases, better already to assign boundary conditions when exergy losses merged with destruction, and we have no term of exergy losses for the components, for each component. And definitely exergy destruction of the system, it is sum of the exergy destructions within each component. I think this is clear. And again, we will repeat that exergetic variables, it is the value of exergy destruction, value itself, the value of exergy losses, exergetic efficiency, which the best way to discuss it is product over fuel. Of course, it can be rewritten using different terms, but in order to avoid any misleadings, better to write product over fuel. And now we have relative terms. We have exergy destruction ratio within the component, and we have two equations. One equation, it is exergy destruction within component over exergy fuel for the overall system. Because we already discussed it, how exergy can be destroyed. It is destroyed the part of incoming exergy, but now we can say absolute precise, it is part of the fuel of the overall system destroyed within component because of irreversibilities of component. And other term, it is also exergy destruction ratio, but it is only percentage of exergy destruction within component over exergy destruction within the overall system, and the result will be absolutely the same if we will apply the method of entropy generation for component and for the overall system. This equation will not bring us any benefits for analysis, but just for illustration purposes, we can see which component contributes more to total irreversibilities within the system and which components contribute less. And similar term, it is exergy loss ratio. So how much exergy of fuel is lost because of exergy transfer to the environment. This value is very important, but only, of course, for the entire system. And finally, we are reaching the equations that we already mentioned several times. We know that there are 4 equations that should be answered in order to evaluate energy conversion system. And only 2 equations can be answered, the first and the fourth, with the variable energy efficiency, the first law of thermodynamics. And the last equation, which variable should be used to compare dissimilar components within within one system, it is entropy generation. And two other questions cannot be answered using the variables from the first and the second law of thermodynamics. But using the exergy analysis, we can answer all questions. As I already promised you, we have all these variables in exergy analysis. So characteristic of the system. From exergetic point of view, we can calculate exergetic efficiency of the overall system. Everything which is related to similar components within the same system or within different systems, it is exergetic efficiency of the component. And the last question can be answered using two variables, exergy destruction and exergy destruction ratio. So now we know that all equations that required to be answered by engineers, we can find answers and we can evaluate everything using the exergy concept. How to apply these variables, what is the meaning of these variables for evaluation of each particular system, we will discuss later. So, and later it is exergy analysis part 2. This is our next lecture. If you found this lecture interesting and useful, please give a like to this video. Please subscribe to the channel and share this link with your colleagues. Thank you.